We can start the session, sir.
Okay. Good morning, everyone. Topic is aromaticity. So in today's class, we'll learn how we can find whether the compound is aromatic, anti-aromatic, or non-aromatic. Okay. So first, some conditions are necessary conditions are there, but you need to remember. First thing, the compound should have a cyclic structure. Cyclic cloud of delocalized delocalized pi electron. Okay. Second thing, it should be planar. It should be planar. If someone asks what is the reason, I'm writing the reason here. That complete delocalization of pi electron is possible only if the ring is planar. If the ring planar means all the bonds must be on the same plane, so that they must allow the overlapping of p orbital. Okay, is planar to allow cyclic overlap of p orbital. Cyclic overlap of p orbital. And third conditions is it should contain 4n plus 2 pi electron, where n is equals to 0, 1, 2, 3, etc. If we are using the system 4n plus 2 pi electron and we are getting the value of n as 0, 1, 2, 3, not in fraction, not in negative, then the compound is aromatic in nature. But if it is not following any of these conditions, the compound is said to be non-aromatic. And second condition is if it is forming 4n rule, not 4n plus 2, then it is called anti-aromatic. Okay. Some conditions are also there. The fourth condition we can say that the carbon in the ring should be sp2 hybridized. And in some cases, occasionally we can say some cases are there sp hybridized. Okay, so you can see if double bond is present, obviously it's a sp hybridization. sp2, sorry. Fifth point, what you need to remember is like okay, 4 point is quite enough. Just don't go for that much rectification and all. I will do the example. It's okay. Some example I'll do, some example you will do. Okay, first we'll see this particular system. See, first condition was the compound must cyclic. This is cyclic. Very good. It's okay. All the atoms are on the same plane, so the planarity is present in the compound. Okay, and third thing is Huckel rule. So if I'll use Huckel rule over here, 4n plus 2 equals to pi electron I'm using over here. 4n plus 2. How many pi electrons are there? See, you can remember like one double bond is equals to 2 electron. One minus sign is also equals to 2 electron. Okay, so three double bonds are there. If one double bond is equals to two electron, if three double bond are present, it means we have six electron. Now just calculate the value of n. 4n plus 2 is equals to 6, then 4n is equals to 6 minus 2. 4n is equals to 4, n is equals to 4.4, that is equals to 1. So the n value is 1, and I told you if the value is 0, 1, 2, 3, the compound is aromatic in nature.
Aromatic.
Yes. So got my point now? Okay, let's see one more example. I'm taking naphthalene molecule. Okay, so the bond are like, first you need to see the conjugation also. Okay, there, see, we can see here double bond, single bond. Take then double bond, single bond, double bond, single bond. And if I'll go like this, double bond, single bond, double bond, single bond, double bond, single bond. So the conjugation is present in the compound. If the conjugation is present, then we'll move further. The compound is cyclic, the compound having the conjugation, sp2 hybridized carbon is present. And the third thing what you have to do that is it should have planarity. So right now I'm saying the compound I'm using right now all are planar. Okay, so now let's move with the compounds with the Huckel rule. 4n plus 2 equals to pi electron. How many pi electrons are present here?
10.
10. Very good. 4n plus 2 is equals to 10. 4n is equals to 8. N is equals to 2. So is this compound aromatic or not?
Yes, sir, aromatic.
This compound is aromatic. Okay, let's take an example of this compound. Yes, this compound is we have in this particular compound we have this conjugation, double bond, single bond, positive side, single bond, double bond. Conjugation is there, cyclic is there, compound is planar. So first we'll use what? 4n plus 2 equals to pi electron. How many pi electrons are present?
2, sir.
2.
2, sir.
Then 4n plus 2 is equals to 2. 4n is equals to 2 minus 2, 0. N is equals to 0. This compound is aromatic, anti-aromatic or non-aromatic?
Aromatic.
This is aromatic. Very good. Okay. Now I'm giving you one example. You have to tell me. Yes. This compound and this compound also. Yes. Third compound. Conjugation is present. Double, single, minus sign, single, double bond, single bond. Conjugation is present. And the same compound, same conjugation is present. Both compound are planar in nature. But let now apply the Huckel rule. If Huckel rule is not applicable, then go for the that 4n rule, that is anti-aromatic rule. Then if both the rules are not satisfied, then go for the non-aromatic. Yes, the first compound is aromatic or non-aromatic?
Non-aromatic, sir.
Aromatic, sir.
Someone is saying non-aromatic, some saying aromatic. Okay, let's check. 4n plus 2 is equals to, see, I can see 6 electrons, 2 double bond, 1 negative sign, between 6 electrons, 6 electron system. Okay, 4n is equals to 4, n is equals to 1. The compound is aromatic in nature. Okay, second one compound. Let's 4n plus 2 is equals to 4, 4n is equals to 2, n is equals to 1 upon 2. So if I'll use this Huckel rule, according to Huckel rule, it's not aromatic. So I'll use 4n rule. 4n is equals to 4, n is equals to 4 upon 4, the compound is 1. So this particular compound is anti-aromatic. Okay, this compound is anti-aromatic. Okay, I'm giving you one more example. We have to do a lot of example today. Okay, this is example number, I don't know. Okay, right now I'm using one. Second example I'm giving you. Yes, first one. First one, n is equals to. First one is aromatic.
Non-aromatic, sir.
Non-aromatic, sir.
What about anti?
Excuse me, sir.
This is
Aromatic.
anti-aromatic. 4n is equals to 4, n is equals to 1. This is anti-aromatic compound. Okay, next one.
Aromatic, sir.
Let's check. 4n plus 2 is equals to 2, 4n is equals to 0, n is equals to 0. This compound is aromatic. Very good. Okay, third one. Yes, third one. See, outer pi electrons are not counted. So the inner one you'll count. We have 6 electron system. This is pyridine. The name of the compound is pyridine. And if I'll do 4n plus 2 is equals to 6 electron, 4n is equals to 4, n is equals to
Aromatic,
1.
sir.
The compound is aromatic in nature. Okay, next one. Then what is the name of this compound? No one revised. Phenanthracene.
Phenanthracene, sir.
Very good. Phenanthracene. Okay. 1, 2, 3, 4, 5, 6, 7. 7 double bonds. All are in
Aromatic, sir.
conjugation. 4n plus 2 is equals to
Aromatic.
14. Let's check. N is equals to 12.4. That is equals to 3. The compound is aromatic in nature. Okay. Next is this is cyclooctatetraene. Okay. If I'll go with the aromatic rule here, if I'll use Huckel rule and all, before that, let me tell you one thing. cyclooctatetraene compound having a tub-shaped structure. Tub-shaped structure. Okay. So the main structure is like this. So generally, this compound is non-planar. All the bonds are not on the same plane. And if the condition is not satisfied, I told you, if the conditions are not satisfied, the compound is considered as non-aromatic. Non-aromatic. So cyclooctatetraene is non-aromatic compound. But if I talk about this compound now, this is cyclooctatetraene. Cyclooctatetraenyl. Tetraenyl dianion. Two negative charge are there. So this particular compound became planar now just because of the negative charge. Now tell me how many electron system and what is the condition? Is this aromatic or is this non-aromatic?
Aromatic system.
Yes, this is 10 electron system now. 4n plus 2 is equals to 10. 4n is equals to 8, n is equals to 2. Now this compound will be considered as aromatic. Clear?
Yes, sir.
I'll give you one more example. You can start doing, okay? I'm giving you the compound, you can start doing. Yes, first one is known as what? Benzene. This is not benzene, this is benzene. See, outer pi electron is not counted. I told you, outer electrons are not counted. Inner electrons. So again, it will be a 6 electron system. 4n plus
Aromatic,
2
sir.
is equals to 6. 4n is equals to 4n is equal.
Aromatic.
The compound will be aromatic. Okay, next one. This one. 4n plus 2 is equals to
Aromatic, sir.
how many electrons?
14, sir.
4n is equals to 12. N is equals to, speak, 3.
3, sir.
Compound is aromatic in nature. Next one. This compound, see, the name of this compound is phenylene anion. Name of this compound is furan. Name of this compound is thiophene. Okay, if that is furan is aromatic or not?
Hello?
Yes. Furan is aromatic or not?
No, sir.
No. 6 electron system is
Aromatic,
there.
sir.
4n plus 2 is
Aromatic.
equals to 6, 4n is equals to 4, n is equals to 1. Aromatic is there. Okay, thiophene. Again, 4n plus 2 is equals to 6 electron system, 4n is equals to 4.
Aromatic, sir.
Again, this is aromatic. Very good. Okay, so let's take last few example. Yeah, this much is okay. The example. Okay, just do these two.
First one, aromatic, sir.
First one is aromatic.
Aromatic. Anti-aromatic, sir.
Anti-aromatic, sir.
Yes, 4n plus 2 is equals to 4, n is equals to 1. This compound is anti-aromatic. Okay, next one.
Aromatic, sir. Next.
Aromatic, sir.
Yeah, 4n plus 2 is equals to 3, 4, 5. It means 10
10.
electron system. 4n is equals to 8, n is equals to 2. Aromatic. So now I think you can find which compound is aromatic, which compound is non-aromatic. Clear?
Yes, sir.
Okay, stability order, just remember who are more stable. So the aromatic compounds are the most stable. Then conjugated non-aromatic. Those compounds which are conjugated but they are non-aromatic. Then after that we have a non-conjugated compound. Non-conjugated compound. And then at last we have anti-aromatic. Okay, so this is a stability order, just remember that. Okay, so now we have completed the first chapter of organic, that is some basic principles of organic chemistry. Clear this much? Yes.
Yes, sir.
Yes, sir.
So now we have to start with the 11th chapter in your book, or the second chapter of organic, that is isomerism. Basically, it's a part of basic organic chemistry, or you can say general organic chemistry. Okay. So let me start with the isomerism. Okay, what are isomers? I think you have learned that in the lower classes. No one knows what is isomers. What are isomers?
So,
Yes.
They have same formula but in structure different.
Okay. So basically, in the lower sections, we used to learn that compound, those having the same molecular formula but different structure, they are known as isomers. See, they are known as structural isomers. Okay. Simply, we can say the compounds having the same molecular formula but differ in their physical and the chemical properties. Okay. Or you can say different arrangement of the atoms. So they are known as isomers. So isomerisms are basically divided into two categories. This is quite a big chapter again. Most probably will finish this within 3 classes max to max. Okay. Not as big as the last chapter was. So we'll finish this particular chapter within, I think, 5 days. Five, not five more, not five, or you can say 3 days. Sure, most probably. So isomerism is basically of two types. First one is the structural isomerism. This is also known as constitutional isomerism. Okay. Second category is configurational, or you can say a stereoisomerism. So compound having the same molecular formula but different arrangement of atom, that is called structural isomerism. Compound having the same molecular formula but have difference in the three-dimensional structure, that is called configurational or stereoisomerism. So if I divide this structural isomerism, this is divided into the categories. First one is chain isomerism. Second one is position isomerism. Third one is ring chain isomerism. Fourth one is functional isomerism. Fifth one we have metamerism. And then we have tautomerism. If I start with the configurational isomerism, we have three categories only. First one is the geometrical. Second one is the optical. Third one is conformational. Okay, so we have certain categories. So we'll start this particular topic now with the first type, that is called structural isomerisms. Structural isomerism. And what is the definition? Compounds having same molecular formula but different structure are known as what? Structural isomerism. So in the structural isomerism, first category we have chain isomerism and also known as nuclear isomerism. Okay, what are chain isomerism and nuclear isomerism? A compound which have the different number of carbon in the chain. For example, I'm taking C5H12. So first you'll make the basic structure CH3, CH2, 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 CH3. So this is the example of a normal chain structure. So it's normal, so we say it as N-pentane. See, we are naming it as N, then iso, then we'll go for the neo condition. What I can do, I can take this any of the carbon on the mid carbon. So it will be CH3, CH2, CH. Above it, I'm taking CH3, then CH3. So you can see here also 5 carbons are present and hydrogens are again same. So if one of the carbon is present above as a side chain, so this is known as isopentane. What I can also do, like CH3, C above CH3, lower CH3 and right side CH3. See, again if you'll see, number of carbon are 5 and number of hydrogens are also same, 12. So what exactly happened? The carbon is present above and below both sides. So this condition is known as neopentane. Just you need to add, if the normal straight chain, then we'll use N. Then one of the carbon is above, then you'll use iso. And on the all the sides is substituted by the carbon, then you'll say neo conditions. So these type of isomers are known as what? They are known as nuclear isomers or chain isomers. Okay, got it. Yes, understand my point or not?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Next, let's start with the position isomerism. Positional isomerism. See, what it will have? Compounds having same molecular formula, but differ only in the position of multiple bond or functional group. See, compound having the same molecular formula, but either the position of double or triple bond is different or the functional group position is different. So we'll consider that type of isomers is known as positional isomerism. So let's see some example. Like I have CH3, CH2, CH double bond, CH2. What is the name of the compound? Just tell me the name fast. Of both the compound. First compound is known as what?
So it is
Butane.
butene, sir.
But
Butene and butene.
one in. Okay,
Yes.
second one. Second
Same.
one.
So
Same.
it is butene.
Butane.
Sir.
It's butene. So if you'll see but one in, but two in, what is the difference? Only the position of double bond is different. Resting are same. So that is known as what they are known as. They are known as position isomerism. Sorry. They are known as what? They are known as position isomers. We can take one more example: CH3, CH2, CH2OH, and CH3, CH, CH3, and above it I'm adding OH. Okay, what is the name of first compound?
Propanol.
Propane 1-ol. Second condition, propane
2-ol.
2-ol. The position of functional group is different only. The rest is same. So we can have one more example. We can take more example of your book then. Okay, in case of aromatic compound, we can also do that. Okay, I'm making CS3 and here we have NO2, orthonitrotoluene. Then we have metanitrotoluene. Then we have paranitrotoluene. So if you'll see all these three examples, all having the same molecular formula, one CH3, one CH3, one CH3, all have benzene, all have NO2 group. But the position of NO2 group is different in all the three compounds. So that type of isomers are also known as what? Position isomers.
Isomerism.
Positions isomers phenomenon is called position isomerism. Okay. Okay. Compound molecular formula is C3H6O2. Okay, the compound can be CH3, CH, CHO, OH. It can be CH2, OH, then CH2, then CHO. Okay, name of both compound fast. See, the position of OH is changed just. Tell me the name of compound fast.
Propane to all.
Propane 2-ol. We don't have aldehyde group. So it is 1, 2, 3, 2 hydroxy, 3 carbon,
Butanoic acid.
propanol, 3 carbons are
Propionine
present.
acid, sir. Yes, sir.
Here 3 hydroxy,
Propanol.
propanol. Don't need, there is no need of revision, okay? There is no need of revision. Now I'll not say just revise. Just because from past 10 to 15 days, I think I'm saying revision, revision, revision. Now I'll say don't revise. Just because you are not revising, so it's okay. Don't revise. Next type of isomerism is functional group isomerism. We'll do functional, we'll do ring, we will do meta today. We will start with the tautomerism tomorrow. Okay. Whether the class will be done or not. Functional group isomerism, if I'll say, okay, I don't think that we can go for this much also. Functional group isomerism, first we'll start functional group having the common molecular formula, same but different functional group. For example, first category I'm taking alcohol and ether. Alcohol and ether. Formula I'm using right now is for example ethanol. Okay, formula is CH3CH2OH. This is ethanol and one is CH3OCH3. This is called methoxymethane. If you'll see both the compound, both have same number of carbon, hydrogen and oxygen. But still what exactly happened? There is a change in the functional group. One having the alcoholic group while the other having the ether group. So such compounds having the same molecular formula but different functional group are known as functional isomers. And the phenomenon is known as functional isomerism. Okay. Second example we can take of aldehyde, ketone and unsaturated ether. Okay. For example, we have CS3, C double bond O, single bond CS3. Okay. With this, we have CS3, CH2, C double bond O, single bond H. We have CH2, double bond CH, single bond CH2OH. I think all the compound having this 3 carbons, if I'll count the hydrogen, 3, 3, 6, 3, 2, 5, and 6, 2, 3, 4, 5, and 6, 1 oxygen. Okay. If you'll see the 3 compound, first one is propanone. It's a ketone. Second one is propanol. Third one is prop-2-ene-1-ol. So if you'll see all the 3 compounds, they all are. Okay, one more compound we can make ether. CH2 double bond CH single bond O single bond CH3. It is methoxyethene. Same. So it can be unsaturated alcohol, or you can say like unsaturated alcohol also here. See, you can see the molecular formula of all the compound is same. That is C3H6O. And we can make 4 compounds, but the four functional group are different. So that type of compounds are known as what? Again, functional isomers. Second, third type we can take carboxylic acid. Carboxylic acid and esters. If you'll see, You can take example CH3 C double bond O single bond OH. This is called ethanoic acid. Ethanoic acid, if I'll make another compound HC double bond O single bond OCH3, this is called methyl methanoate. This is a ester. So this molecular formula is same, but the structure is different. Fourth type we can take of alkyne and alkadiene. But okay, I'm taking a good example, that is cyanide. Cyanide and isocyanide. This is easy. CH3 C triple bond N, or just directly you can write CH3CN, and another one is CH3NC. This is methyl cyanide. This is methyl isocyanide. So we have two things, same molecular formula but different structure, but different functional groups. of functional group isomerism. Okay, we can take another example of nitroalkene and alkyl nitrite. Nitro, it means we are using NO2 group. Nitrite, we are using ONO group. Okay, so structure will be, for example, I'm taking C2H5 N double bond O single bond O. Another example, I'm taking C2H5 C2H5 O NO. So if you'll see, both compound having the same molecular formula, but again that double bond is, that position of functional group is different, or if you can say if the functional group is different, so they are known as functional group isomerism. Okay. The last type I'm taking of functional group is aromatic alcohols. Aromatic alcohol, phenols and ether. Okay. Okay, take this compound. Benzene, over it we have CH2OH. First one compound is known as what? Benzyl alcohol. Anisole. So see, both have benzene ring, both have one carbon, both have 3 hydrogen, both have 1 oxygen. Molecular formula is same, but the functional group, one having the alcoholic functional group, another one having the ether group. So they both are known as, again, functional isomerism. See, you guys are not revising the IUPAC. I think that's why you still don't know what is this benzyl, benzo, and benzyl. Okay, next type is ring chain isomerism. Ring chain isomerism. So the compound having the same molecular formula. Okay, same molecular formula, but mode of linking is different. Mode of linking is different. That is, forms a ring. जो ring बनाएंगे. For example, we can see C3H6. We have this compound. So we can 3 carbon 1, 2, 3. So we can make this compound CH3 CH double bond CH2. This is called prop1ene. Or else I can make one compound CH2 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 and ring formation. This is called cyclopropane. So if you'll see, both compounds having the same molecular formula, but the linkage is varying. One is forming a straight chain while other one is forming a ring. So when there is a formation of ring takes place, so that type of isomerism is called ring chain isomerism, just because it is between the ring and the chain. One more example I can take of C4H8. The compound can be CH3 CH2 CH double bond CH2. If you see this compound, this is called but1-ene. But if I want to make the compound CH2, 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 four cyclic ring, carbon cyclic. This is known as cyclobutane. So this sort of examples are of the ring chain isomers. Clear? Yes, any doubt? Till
Yes,
now.
sir.
Okay, so the last for today is metamerism. Okay, generally the compound having the same molecular formula but having different number of carbon on either side. Having different number of carbon on either side of functional group. Okay, generally this happen in the functional group which are bivalent. Okay, you can say join from the two side. For example, I'm taking C4H10O. So we can make like C2H5O, C2H5. We can go C3H7O, CS3. So both having the same molecular formula, both having the same functional group. One is diethyl ether. Another one is methyl propyl ether. Okay, you can say, or you can say methoxypropane. So if in both the compound you can see on the either side, if it is having the same number of carbon on the either side in first condition, while on the second condition you can see they are having the different number of carbon on the either side. One having 3 carbon on the left side, right having the 1 carbon. So such compounds are known as metamers. These compounds are known as metamers just because they are showing the metamerism. One example we can also take of C5H10O, C2H5, CO, C2H5. This is called diethyl ketone. We can take another one, C3H7CO, CS3, that is again methyl propyl ketone. So this is again example of what? Metamerism. Okay, so we can take more example like C4H11N, that is C2H5NH, C2H5. This is called diethyl amine. And we can take another example C3H7NHCH3. Number of carbon on the either side is different. Name methyl propyl amine. We can take one more example CH3 CH2S CH2 CH3, that is diethyl ether, diethyl thioether, just because S is present, thioether. Okay, we can make another example. It can be like CH3S CH2 CH2 CH3. The name will be methyl and propyl iso thioether. Okay, so you can see both the example having the same molecular formula. As thioether I'm taking, so they are known as what? Metamers. Okay, general formula C4 3 to 4 3 to 5 6 7 8 9 10. It's 10 S. Okay, so such compound are known as what? Metamers.
Metamers.
Metamers. And the isomerism is known as
Metamers isomers.
metamerism. Metamerism. Okay. Next one is tautomerism. We'll do this tautomerism from the next class. I'll not start just because it's a quite big one and we also have the types. So we'll start with the tautomerism tomorrow in the class. Then we'll start with the geometrical isomerism. Then we have optical isomerism. So you can see we have completed a lot today, and we have started a new chapter also. So we have done chain, we have done position, we have done ring, we have done functional, we have done metamerism. So only the tautomerism is left in the structural, and then we have to go with the geometrical and optical. So it will take maximum 2 or 3 classes, and the chapter will be done. Okay. So then this Saturday you'll have a test of this particular chapter. You can go for the aromatic compounds. Okay. So then next class, on the next week, I think probably, but I have only tomorrow class, I think. Yes. So maybe this week will not complete this particular chapter, but most of the portion I'll complete. And from the next week, we have to start with a new chapter that is called purification and the characterization of the organic compounds. That is quite important chapter. And so too much theoretical, not that much theoretical, you can say numerical based. So we'll do numerical in that particular chapter. You have to do the estimations. So this much is clear, I think. Aromaticity and 5 type of isomers are we have done. Any problem? Any doubt? See, I'm showing you one by one. This is chain. This is position. This is functional group isomerism. And this is ring chain. This is metamerism. This is, now we have to start with the last one that is called tautomerism. How much time we have? We have 3 minutes. We can at least write the definition of this particular type also. Okay. So if I talk about this particular isomerism, it's a special kind of function. This is a functional group type, but it's a special type of functional group. Okay. You can write a special kind of functional isomerism. So this is you can say a part of functional group isomerism that exists in dynamic equilibrium. This exists in the dynamic equilibrium. It means interconvertible states are there. Why this happen? It arises due to migration of hydrogen. The migration of hydrogen atom from polyvalent atom to the other. From one polyvalent atom to the other atom, this will transfer. So that type, the isomers form. The isomers form are known as tautomers. And phenomenon is called tautomerism. Okay, basically tautomerism is of 2 types: dyad system and triad system. Okay, so in dyad system 1-2 migration is there. Triad system will talk about the many types. So at least do this much in the tautomerism today. So sort of functional group isomerism. Just what happened, this exists in the dynamic equilibrium. The states what we'll get with, they are in the random changeable state. Why this tautomerism occur? Just because of there is migration of the hydrogen atom from one polyvalent to another polyvalent. And such type of isomers are known as tautomers, and the phenomenon is known as tautomerism. Okay, 2 types: dyad system or triad system. So we'll go for the dyad and triad system tomorrow. In the tomorrow class, we'll finish this particular thing. We'll go with the stability of the compound, steric hindrance factors also. Then we'll go start with the stereoisomerism. Okay. So thank you for today. Revise this lesson first. At least revise and do the questions of the aromaticity also. I'll see you in the next class. You
Thank
can,
you, sir.
yeah, thank you.
Yes. The students, you can join the next session.